Okay, so this week we're going to circle back a little bit actually. So this is going to be a little bit of the acid strength trends from last week. It was just an example. I didn't really feel like there was time for, things were getting a little bit long, so I pushed it to this week. So, and it's a really good example of the relationship between the strength of a weak acid and the strength of its conjugate base. So as the weak acid gets stronger, the conjugate base gets weaker, because one thing is it can be more stable, and so it's not needing that H plus on it as much. And so this is a great example of that. And so generally, we'll just start out. Here's the general trend. And I'm always just covering my bases there, right? Because chemistry, there's always something that breaks it, like every trend somewhere. But generally, more oxygens on our anion equals a stronger acid that would be made from it. Could be a strong acid, could be just a weak acid with a larger Ka, right? It has more dissociation. And the example here actually has one of both, HNO3, nitric acid, and HNO2, nitrous acid. And so these are, if we ignore the H's, that'd be NO3 minus nitrate and NO2 minus nitrite. And so those are oxoanions because they have an element with oxygens on them, and they are an anion, so they have negative charges, which means that we can put H pluses on them and we get a compound, right? And these are acidic compounds. And so in the case of HNO3, based on our trend, we'd expect this to be a stronger acid than HNO2. And in fact, it's not just a stronger acid, but it is by itself a strong acid. Fun with words, right? So this is a strong acid. Okay, and so HNO2 is not a strong acid. It's actually a weak acid, which fits our trend. And since it's a weak acid, let's throw the Ka value up here. So 4.5 times 10 to the minus 4. So there's a definite change in acidity here. Now why? Why does this happen? Right, let's just jump right into the most dangerous question of them all. Why? What is the reason here? Why does this give up its proton, its H plus, to solution more readily than this? And then not try to take it back. Right? This is also not, once that H plus pops off, it just floats around as NO3 minus, and it's content to be that way. Versus the NO2 minus, which turns out the majority of them are actually going to be bringing that H plus back and floating around as HNO2, because we have a Ka value that is much, much, much less than 1. So we need to look at the structures. And then we will see that there's what we call resonance. There's a blast from the past for you. Stabilization. So the anions have a resonance structure. And the more resonance there is, the more stable they are. The less they need that H plus back. The weaker of a conjugate base they're going to be, the stronger of an acid the weak acid's going to be. So if we look at NO3 first, NO3 minus, remember, our resonance structures have these dashed lines, so it means it's more than one bond. But what is it? Well, these are 1 1/3 bonds. Okay, and so that negative charge, there's a -1 charge being shared. So each of these is about a -0.33. So all of the oxygens are like a -0.33. They're basically, there's a negative charge and they are sharing the load. Everyone's kind of grabbed a corner and they're lifting together. And so it's not as heavy. It's not as big of a deal to handle. And so there is a negative charge. Would that attract an H plus? In theory, yeah, but it turns out it's small enough in any location that it doesn't really do that. So that resonance, the fact that there's 2 single bonds and a double bond that are being spread around, or well, I guess 3 single bonds, and then there's also one of these would also be a double bond, so they end up being a 1 1/3 bond, if you remember your resonance stuff. That weird little detail there. That's stable. That's that. You know, the ability to do that is a stabilizing force, and this is really important in organic chemistry. You'll see, you know, any weird behavior. Seems like more often than not, resonance is behind it. Now, if we look at NO2, minus, there's only 2 resonant bonds. And so each of these oxygens, again, are sharing the load on this negative charge. And so now they're about a negative 0.5. That's a larger negative charge. That's going to have a stronger attraction to a plus charge of a hydrogen ion. Right? H plus is going to be more attracted to the negative minus. And it's not like a linear relationship. There's all kinds of factors in it. And so that causes us to jump from something being a strong acid, where it just drops the H plus and never takes it back, to weak acid, where more often than not, it's going to take that H plus back. So, you know, that's why you only have a little bit of stuff on top, only a little bit of H3O plus, only a little bit of NO2 minus, and a lot of HNO2 on the bottom of our Ka expression here. And it's because of that difference in charge. It's the resonance. So the resonance structures, this is a more stabilized structure than this one. So this is a more stable conjugate. It would be a conjugate base if it was actually acting as a base, but it's a more stable anion. And this one's a less stable anion, so it acts as a conjugate base to unionize itself, if you will. If any of that makes sense. But it's a good example. So just in general, you know, if something's a strong acid, that means it has a really stable anion that forms and doesn't act as a base. And if something is a weak acid, it has a less stable anion that is going to try to pull back that H plus that left, and will, and act as a weak base. And the less stable this is, the stronger of a weak base it's going to be. All right. So the last thing I'll talk about is the mathematical relationship between Ka and Kb. This might also help illustrate this relationship a little bit better than I talked about it last week. And so if you have Ka for your weak acid, and you multiply that by Kb for the conjugate base, so you know, if this was our weak acid, we've got a Ka value. This is our weak base right here, NO2 minus. It would have a Kb value acting as a base. If we multiply these by each other, we get Kw, which is just 10 to the minus 14. Okay? And so what this is showing is the exact relationship we talked about. So as an acid gets stronger, Ka gets larger, which means Kb must get smaller because the product is the same every time. And you know, conversely, if an acid gets even weaker, the conjugate base value is going to get stronger. Kb is going to get larger as Ka gets smaller. And again, we just get that same product at the end. So they are balanced with each other. Now, if we look at Kb for NO2 minus, we have everything we need to calculate it. Okay? We've got our Ka value up here. Oh, you thought I just wrote it for fun earlier? Ha! There was a reason. There's always a reason I do everything, even when there's not. And so we can calculate that. And so it's going to be Kw. We just divide Ka over here, right? So it'd be Kw over Ka. And so that's going to be 10 to the minus 14 over the Ka for HNO2, right? The acid that goes with this conjugate base. And so that's 4.5, as we talked about before, times 10 to the minus 4. And we calculate that out. and it comes out to be 2.2 times 10 to the minus 11. Okay. So, there it is. What else is there to say here before I close this video? Oh yeah, so what about KB for NO3? What's that going to be? Well, it's just 0. Because HNO3 is a strong acid. So strong acids don't play these equilibrium games, right? They just it's like we talked about 151. It's like I got reactants, I got products. That's what they do. Reactants, boom, products, done. No backwards reaction, no conjugate base, no KB value, none of that. Boom, we just make H3O plus, end of story. Don't get it on your arm. You know, so on and so forth. This is the one I'm sure I talked about at 151 if you had it with me. But HNO3 is the one that, you know, so it'll burn you like an acid. Obviously, it's a strong acid. But it also will stain your skin brown. And so I only got a little bit on me, and I learned it from that. And then it came into play later in my career with someone else. But again, I think I told that story in 151, so I won't tell it again. You can fish through my 151 videos if you really want to hear the story. All right, so again, this is really kind of, you know, wrapping up last week, and so we're gonna start talking about just dissolving new things and how they affect pH this week. And to start that out, we'll talk about salts. So certain salts can affect pH when you dissolve them, and so I'm gonna break that up into 3 videos. It's gonna be one section together. I'm gonna try something a little different formatting wise. Like it'll be one practice sheet for all 3 of those videos. But I'll break the topic up. So we're going to talk about hydrolysis of salts next.